Hello everyone, welcome to the first lecture of the 7th module, which is on resistive random access memories or RRAMs as you may know it. The disclaimers remain the same. So what exactly are resistive RAMs? So resistive RAMs are metal insulator metal kind of structure. So let me write that. So they are metal insulator metal memcap kind of structures where a layer of insulator is sandwiched between two metal electrodes. So in this diagram, those two metal electrodes happen to be platinum and that insulator happens to be TiO2 minus X. So I'll come back to that point why it is not TiO2 perfect stoichiometry but TiO2 minus X. So these oxides have a unique property that you can transit from this insulator state to some conductive states, and you can reversibly switch these oxides between several conductance states, between a maximum conductance state and a minimum conductance state. So this kind of a switching behavior of oxides is not new. So in 1960s itself, people observed this abrupt switching or transition of oxides from insulator to conductive states. However, with advent of fabrication technology in 1990s, people started showing different kind of these resistive RAMs, or I would say different kind of switching behavior in oxides. And what were those oxide materials? So mostly they were complex material, like complex oxides, like perovskite. So what are common perovskite materials? So it can be strontium titanium oxide, it can be strontium zirconium oxide, etc. And people also saw this kind of a switching in binary oxides. So these are complex, like perovskites are having more than 3 components, so it's kind of a complex kind of oxide. So they also saw this in binary metal oxides. So they also saw this kind of phenomena in binary metal oxides. Which were the oxide materials? So they saw it in nickel oxide. They also saw it in titanium oxide. And the best part about these transition metal based metal oxides is that they are compatible with CMOS process. So taking advantage of that, in 2004, Samsung actually came up with first memory demonstration of RRAMs. And what they did was they used a nickel oxide based RRAM on top of 180 nanometer CMOS technology. And this kind of revolutionized this field. I mean, this was the first demonstration and it kind of brought attention back to the resistive RAMs. Then people started experimenting with different metal stacks and all those things. So what are the common names of these resistive RAMs? Like in your papers, you'll find RRAMs as one of the common names. Then you'll also find oxide-based RAMs or OXRAMs, or even an acronym which is RERAM. So you'll find these, and RRAM is always there. So you'll find that these kind of devices are common in your research papers by these 3 acronyms. Now, what are the properties that make them so lucrative? So one of the property that makes it so lucrative, as I already discussed here, that similar to PCM, devices, even RRAMs are CMOS compatible. And what that means? That means simply that they can be integrated on top of front end of line, that is on top of transistors. Now how they can be, so there can be different ways of integrating it on top of transistors, and that kind of configuration is called a 1T1R configuration, one transistor, one resistor configuration, which is shown over here. So here you have a MIM structure, which is a RRAM integrated on the top of drain of a MOSFET. So this is called one transistor, one resistive kind of configuration. So this is one way in which it can be integrated. So let me write that. So first, it can be integrated directly over source drain plugs or contacts. So usually the source drain contacts or plugs are tungsten. Here it's copper because here it's a metal layer 1 which has been used. But usually it's tungsten, which is the source drain contact plug. So if you are using tungsten, then you can go ahead with WOX or tungsten oxide based memories. And another point that I wanted to clear is, why do we use X instead of WO2? So the thing is, in these devices, we have defects or we have absence of these oxygen atoms. They are not present in stoichiometric ratio. So that is the reason why we use X instead of exact WO2 or or TiO2 or something like that. We always use TiOX, NiOX or WOX. So this is one way in which it can be integrated on top of your MOSFETs. However, in this kind of configuration, your effective density is limited by size of T, right? Since this is monolithically integrated on top of this MOSFET, the size of this MOSFET dictates the size of your memory element. So what is the other configuration in which it can be integrated on top of front end of line? So it can be integrated on top of interconnects as well. So we also have here like a RRAM compatible process with 130 nanometer technology of ST microelectronics, where you can integrate RRAMs on top of metal 4 of CMOS. So you make your analog circuits till metal 4 layer, you connect it using M1, M2 and M3 layers, and above M4 you can actually integrate RRAMs. So we have that capability over here, and we'll be kind of fabricating few chips using that technology. So it can also be integrated on top of interconnects. So copper is kind of the bottom electrode in such cases, and you can even go ahead with copper oxide based, RM devices. Now, if they are integrated on top of this interconnects, then they are available in what is known as. So if they are integrated on top of interconnects, then that is called a passive kind of crossbar array structure. Why passive? Because in 1T1R structure, you can control the current through this RRAM by the means of this gate electrode of your MOSFET. So since this is in series with the MOSFET, whatever current is flowing in the MOSFET will flow through RRAM, and the current through the MOSFET can be controlled by this gate terminal. So you have kind of an additional knob to control the current through your RRAM device. However, in your passive crossbar structure, there is no selector. And what happens there is, it's shown over here, like on the top. So you have like these horizontal electrodes, which are the top electrodes running in this direction. And then this is also shown over here. So this is your horizontal electrode or the top electrode running in this direction. And your bottom electrode, so your bottom electrode runs like this in a direction perpendicular to this. And here it comes out of the paper, like here and here. So what you have is, you have a blanket deposition. So let me write that because that's an important point. So you have like a blanket deposition of oxide over patterned bottom electrode. So your bottom electrode is like this, and on top of it you have a blanket deposition of oxide. So this oxide is present everywhere, right? This oxide is present everywhere, and then there is this top electrode going in the horizontal direction. So what you observe here is that at the intersection of each of these top and bottom electrodes, you have MIM structure and you have the RRAM. So let's go at the intersection of top electrode and bottom electrode, you have RRAM devices. So here at each of these points, we have RRAM device. So here so it's something like this. So here the density is high. So the memory density is high. Why it's high? Because here it's actually the size of the RAM device, which is the actual size of the memory element. Unlike the 1T1R case, where the size of memory element was the size of the select transistor. So let's call this passive crossbar. Let me write that here as well. It's passive crossbar, and this is called 1R. Instead of like 1T1R, it's only called 1R structure. Now, what can be done is, even this can be 3D integrated. How? So, what you can do is, here you have a bottom electrode, then you have a blanket deposition. So here you have bottom electrode, then you have a blanket deposition of your oxide, and then you have top electrode. So this is 1R, which is represented here. Now, even on top of this, you can again deposit insulator, and on top of that, you can even deposit a metal electrode. So that becomes another RAM. So these two RAMs share one of the electrode. So the top electrode of the second one, the red one, shares the bottom electrode of the first one, something like that. So this can also be integrated in a 3D form, and this is what this chip shows. And this came from my postdoc group. So let me write that. So we can further increase or stack layers of passive crossbar, and that way we can reduce the density further to 4f square by n, where n is the number of layers. So 4f square is kind of passive crossbar size. So size of one cell in passive crossbar is 4f square, and size of one cell in 1T1R is close to 6f square. So it can be reduced further to 4f square by n if we integrate it in a 3D fashion. So this kind of integration was already shown by my group, and they have successfully programmed and erased all those two layers. So this kind of 3D integration is also possible in RAM devices. Now, let us go ahead. Once we have discussed about the structure of the RMs, let us go ahead and discuss about switching in RMs. So let me tell you very frankly that this is a debatable topic. I would say that the exact mechanism is still not known. However, some stacks like hafnium oxide, titanium oxide, or nickel oxide have been well understood. So let me write some properties about switching of your OXRAM devices. So your switching in OXRAM, or switching mechanism, I would say, your switching mechanism is not only a function of oxide material, but it also depends on electrodes. So this is the first point that you should remember, that just by looking at the oxide material, you should not judge whether it is unipolar or bipolar. I'll discuss about that as well. However, irrespective of the RM device, there's a common definition which goes for the set and reset process. So there are two common terms here. One is the set process. So the set process refers to switching of device from high resistance state to low resistance state. From now on, I will refer this high resistance state as HRS and this low resistance state as LRS. So irrespective of the nature of switching in your RM devices, the set process refers to the process of switching of the device from high resistance state to low resistance state. And similarly, we have another process which is called reset process, which refers to switching of your RAM from low resistance state to high resistance state. Now, one more fact that I'd like to tell you about RMs is, similar to PCM, the as deposited or your virgin RMs do not show reversible switching at low voltages. Low voltages. So in your PCM, you had that ohmic threshold switching, because of which you were able to increase the current and heat the device and crystallize it. Here also, your as deposited or virgin oxides, they will remain in the insulator state. And if you want to reversibly switch it between two different states, what you need to do is, you need to inject some defects in there. So let me write that. So if you want to have this resistive switching, if we want this resistive switching, what we need to do? We need to inject vacancies or defects inside the virgin oxide films. And that process of injecting vacancies or defects is typically what is known as forming. So unless an oxidam device is formed, it cannot be used for resistive switching. I mean, it won't switch, and then it cannot show reversible resistive switching. So this process is called forming, or some people also call it electroforming. Why electroforming? Because it is formed with the help of electric pulses. So what happens here? What happens is, we try to stress the device, applying a high voltage or trying to inject a high current through it, so that we achieve a soft breakdown. And that is the kind of most widely accepted theory behind your forming or electroforming. And then once those defects are injected inside your R ramps, then they form a conductive filament between your two electrodes. And because there's some filament which is connecting two electrodes, the resistance goes down and the device reaches the LRS. And once it reaches the LRS, we say that it has been set, and then you can apply electrical pulses and then perform reset process and then set process again. You can reversibly switch it between the LRS to HRS. However, if the forming is not there, you won't be able to first set you won't be able to put the device into the low resistance state, and you won't be able to perform set or reset process unless you form the device. So forming kind of becomes a bottleneck, or it kind of becomes the most important process for using RRAMs as memory elements. Now, RRAMs can be differentiated based on whether the reversible switching is happening at the same polarity of pulses or at the different polarity of pulses. So let me write it. So RRAMs can be unipolar or bipolar depending on the pulses required, or the nature of the pulses required to switch the device. So there's also one category which is known as non-polar. So I'll be discussing about that as well. So in the case of unipolar switching, so let me just write that as well. So in case of unipolar switching, what happens is the switching direction, I mean whether it's from LRS to HRS or it's from HRS to LRS, the switching direction, that depends on the amplitude only. It depends only on the amplitude of the pulse and not the sign. However, if you talk about bipolar switching, the switching direction depends both on the amplitude as well as on the sign or polarity. So in this case, we have set and reset at different polarities, whereas in the case of your unipolar, we have set and reset at the same polarity. There's another class which is called non-polar switching. So in non-polar switching, what happens is you have unipolar switching for both positive and negative sign of voltages. That is, in both first and third quadrant, your device or RAM shows a symmetric behavior. So now let me discuss these things. Try to understand this unipolar and bipolar mechanisms in detail. So let us first talk about this first picture, which shows your I versus V curve. So you have current on the y-axis and you have voltage on the x-axis. And the first one is called a non-polar configuration. Why it's a non-polar configuration? Because it is symmetric in the first and third quadrants. And the set and reset process both appear for the same polarity of voltages. So if you talk individually about the first or the third quadrant, they are unipolar mechanism. But since these are happening together, so it's a non-polar kind of switching. So what happens here is, let us start with the LRS. So let us start with the LRS. Let us say that the device was in low resistance state. So let us say the device is in low resistance state. So how do we ensure that this curve corresponds to the low resistance state? So in your I versus V curve, the slope determines resistance or conductance. So the slope gives you conductance basically. So higher the slope, higher the conductance, lower the slope, lower the conductance. So higher the conductance means a lower resistance. So higher slope over here ensures or tells you that the device was in LRS. And now what you do is you kind of apply a positive voltage, and for a particular amount of voltage, the device resistance suddenly drops. The device conductance suddenly drops, or the device resistance suddenly increases. So when it reaches this voltage, which is called the reset voltage, what happens is the device resistance suddenly increases, or the device conductance suddenly drops, and it reaches what is called HRS. So how do you ensure that this is your HRS? Because its slope is pretty low, so its conductance is very low, and as such its resistance is very high. Now let us say that we started with this HRS itself. So it will, if you start to apply some voltage on it, so it will try to follow this linear kind of curve because it's a resistance inherently. So it's a high resistance, it's in the high resistance state, you start applying some voltage. Suddenly it reaches a set voltage. This voltage is called the set voltage, and the conductance shoots up. The conductance increases significantly, or the resistance drops significantly. Now, since the resistance is dropping significantly, a huge amount of current will flow through the device, and that current may be enough to generate enough heat to burn out your device. So whenever you have this set process, you need to ensure that you control the maximum current that is flowing through your device, and that you do via the help of this compliance, current compliance. So this is called current compliance. So how do you ensure current compliance? So in 1T1R, since your RM is in series with your MOSFET, so the MOSFET current, maximum current that can flow through MOSFET, that dictates your compliance current for RM. However, in passive RM circuits, you do not have any selector. So in order to control the current there, you have to employ additional analog circuit, or you can do it with the help of your semiconductor parameter analyzer when you are measuring those devices. And that is particularly what we did when we were measuring the RM devices. So we kind of put a maximum limit on the current that can flow through these devices by putting a maximum limit on the current that can be driven by that semiconductor parameter analyzer. Anyway, so you can always use some current limiter in your circuit. So this was about your unipolar or non-polar kind of switching behavior. Now for your bipolar switching, what happens is the set is kind of mostly in the positive voltage and the reset is in negative voltage. So let us start the analysis here. So let us say that the device is initially in the HRS and we start increasing the voltage. So there comes a particular voltage which is known as the set threshold voltage, and at that your conductance suddenly shoots up or the resistance suddenly decreases, and then we control the current through the device by applying this compliance current. Now let us say that we are switching, or we are kind of sweeping the voltages in the reverse direction. So now we know that we are in the low resistance state. So the slope is kind of higher. That simply indicates that we are having a higher conductance or a lower resistance. So you follow this path because it's essentially a resistor. However, when it hits a particular voltage on the negative side, which is called the reset threshold voltage, what happens is the resistance suddenly increases or the conductance suddenly reduces. So once the conductance reduces or the resistance increases, the device switches from the low resistance state to the high resistance state, and this is known as reset process. So in bipolar devices, while the set happens as at positive polarity of voltage, the reset happens at negative polarity of voltage. So there is a difference in the physical mechanism between the two that we shall also discuss later in the slides. So also talk about the different transport mechanisms in your RM devices. So there is no universally accepted transport mechanism, and this is also debated. And the reason behind this is, your different stacks. So what I mean by stack? So one stack is like different combination of electrodes and your oxide materials. So different combination of electrode and oxide material will give you a different kind of transport mechanism or different kind of switching mechanism or a different behavior, I would say, altogether. And it's very difficult to kind of explain all these transport mechanisms using a single theory or unified theory. So this is also debatable. Different stacks will have different mechanisms, and there's no universally accepted kind of a model. However, people know that the LRS can be modeled as a simple ohmic or linear IV. I mean, in most of these stacks, your LRS shows a ohmic or linear IV characteristics. While this LRS is kind of very, I would say, simplistic in terms of IV characteristics, your HRS is actually complex. HRS IV behavior is actually complex. In some oxide stacks, people have seen Poole-Frenkel emission based IV, like Poole-Frenkel emission dominated IV, I would say. Poole-Frenkel emission dominated IV. So in Poole-Frenkel emission dominated IV, you have a relation between I and V as log I by V gets proportional to V raised to power half. So this is the kind of IV characteristics that people obtain for some of these oxide stacks. While for others, they also obtain something which is close to the Schottky emission. So how IV is related in the case of when Schottky emission is the dominant mechanism, you have log I proportional to V raised to power half. While for other stacks, people also found out that there is this space charge limited transport mechanism, which shows linear dependence of IV for small voltages and Child's square law dependence for high voltages. So people also found out that some oxide stacks also show this kind of IV behavior. However, any one of them or any of these cannot explain all the stacks at the same time. So let us look at the different mechanisms which may lead to electron transport from cathode to anode of RMs. So let us look at this figure over here, which shows or which kind of summarizes all these mechanisms. So what can you say about one? So let us take these one by one. So this simply shows the possibility, like possible mechanisms by which an electron can go from a cathode to anode. So let us talk about these mechanisms one by one. Let us take the first mechanism. What is that mechanism? So it's Schottky emission. So what happens in your Schottky emission? You must have seen it in metal semiconductor junctions. So what happens? Your thermally active electrons, thermally activated electrons, they flow over the barrier. They jump the barrier or flow over the barrier. So that is the first mechanism, which is shown over here. Now, what is the second mechanism? Second is nothing but Fowler-Nordin tunneling. We have already discussed a lot about it while discussing flash. What is the third mechanism? So third mechanism is direct tunneling. So these depend upon the dimension of the oxide and the electric field. So if the electric field is high and the dimension of the oxide, the thickness of the oxide is less than 3 nanometers or 4 nanometers, you will observe direct tunneling. Otherwise, it would be Fowler-Nordin tunneling. Now, you will be able to see different states inside the oxide as well. So these are the states inside the oxide. So these are basically indicating the presence of traps. So forming process, as I told you, that forming process induces a lot of traps and defects, and these may aid movement of electrons, right? So what can be these mechanisms because of the traps? So if you look at 4, so 4 is here. 4 is nothing but cathode to trap tunneling, right? So fourth is cathode to trap tunneling. Now that the electron is in the trap, it can also go to the conduction band by this 5 mechanism. So fifth is what? It's thermal emission. It's thermal emission from trap to conduction band of oxide. There can be another mechanism, which is the 6th, and that is what? That is FN tunneling from trap to the conduction band. While still there can be another mechanism where these electrons hop over different traps like this, like shown in 7. So 7 is trap to trap hopping, and if these traps are aligned appropriately, there can also be trap to trap tunneling. So trap to trap hopping or trap to trap tunneling is also possible. And once this electron comes close to this anode, then there can also be a trap to anode tunneling. So these are the different mechanisms by which an electron in the cathode can go to the anode. Now, which one is dominant? So the question arises over here is, which one is dominant? So what is the nature of electron? So electrons always tend to take least resistance path, right? I mean, the current always flows through the least resistance path. So which one of them will give you the least resistance path? The process which offers the highest transition rate amongst these. So which process will give you the highest transition rate? What are the factors on which that will depend on? So that will depend upon first the oxide material. Let me use a different pen. So that depends. So the parameters on which this depends is first the oxide material, then second the fabrication process, because that determines how much defect and all you have injected here. Then it also depends upon your interface quality. Interface quality of what? Interface quality of electrode and oxide and electrode. As we know that the switching mechanism is a property of both the oxide as well as the electrodes. So these are few parameters on which of these mechanisms are kind of going to be dominant depends on. And forming process, apart from forming process, so forming process induces your traps and defects. Apart from that, so let me write it somewhere here. So during fabrication also, if you use limited amount of precursor, let's say you have to deposit TiO2 and you give the system or the tool less amount of oxygen. So the kind of stack that it will deposit will have less amount of oxygen. So instead of depositing TiO2, you'll deposit something which is TiOX. So during fabrication, if you use limited precursors, that way you'll also end up having some amount of traps and defects. So this kind of thing will lead to a forming free device. I mean, if you already have a lot of defects or a lot of kind of traps in your device, then you need not apply very high voltage to induce soft breakdown. You reduce the forming voltage, and in some cases, it also may lead to forming free devices. So let us talk about forming process. As I told that it's very important process. Without this, your RM devices cannot even work. So what forming essentially means is, you start with a virgin device or a pristine device, then you stress it with the help of a large voltage, or you try to inject a large current through it, and then you essentially end up having a soft breakdown, and that soft breakdown leads to connection between the top electrode and the bottom electrode with the help of these oxygen vacancies or the conduction filament. So this kind of thing which connects your top electrode to the bottom electrode is called conduction filament. And once there is something which is connecting your top electrode to the bottom electrode, you end up having a low resistance state, because now there's something which is connecting top electrode to bottom electrode and it can conduct electrons. So the resistance of this oxide stack suddenly reduces and it goes into the low resistance state. That is what is happening in the forming process. So to summarize it, you started with a pristine device, or you started with a Frankenstein monster which was sleeping. You stressed it, you injected a lot of current through it, and then you kind of woke it up. Then you ended up in the LR state and you woke it up. Now let me write all the mechanisms that are responsible for it. So one of the widely accepted theory is that a forming process leads to, so let me write that. So one of the widely accepted theory is that the forming process leads to soft breakdown. So now what does this soft breakdown means? So what it means is, at high enough electric fields, some amount of oxygen atoms, let me write that. So at high enough electric fields, some oxygen atoms are knocked out of their equilibrium position, or are knocked out of their lattice position or equilibrium position, and then they drift towards your anode, right? Since anode is positively charged, right? So this leads to defect generation, right? Now this deficiency of electrons, not the electrons. So let me write that. So once the oxygen atoms have been knocked out and they have already moved towards the anode, it leads to deficiency of atoms, which kind of leads to formation of this conduction filament or the conductive filament. And what constitutes this conductive filament? So this conductive filament, in case of RM devices, it's made up of oxygen vacancies. In your CB-RAM devices, it's made up of metal precipitates. I'll also talk about this metal precipitates. So I'll talk about this CB-RAM in a special lecture on CB-RAM devices. Now, how do we know that this kind of oxygen vacancy forms a filament, conductive filament between the two electrodes? So, the CAFM images of RRAMs after forming process has confirmed that the vacancies connect two electrodes, like your top electrode to the bottom. So here also, first it was experimentally observed, and then to explain that, this theory was given. This theory of oxygen atom kind of migrating towards the anode, this theory was given. And what is so special about this? So the thing which is special about this is that all these as deposited oxides, all these as deposited, or these virgin oxides are not single crystalline, but they are usually amorphous, or they are polycrystalline. And this conductive filament, this starts forming along those grain boundaries, along the grain boundaries of your polycrystalline material. And one more thing is very clear to us, that after this forming process, a large number of defects are introduced. But the defects which are introduced, do all of them participate in the subsequent switching cycles? So the question I raise here is, okay, I generate a lot of defects. Like a lot of defects are generated during forming process. But do all these defects take part in subsequent stitching? So what I mean by that is, you formed a device, you injected these defects, and you enter the LRS. Now, if you switch your device from LRS to HRS, will all of these defects take part in it? Will all of these defects kind of react to your electric field? So my question is, if we go from LRS to HRS now, will all of these defects take part in it? The answer to this is a big no. So the answer is no. So if all of these defects took part in it, then your reset voltage, should have been as high in the opposite direction or the opposite polarity as the forming voltage. But that is not the case. So in terms of magnitude, your reset voltage is actually very less as compared to your forming voltage. So what is the reason for that? So the reason is, let me use red pen for that. So the reason is, only the defects which are close to the electrode, or only the vacancies which are close to the electrode, they take part or they get recovered during the HRS switching or reset process. So now that you have oxygen vacancies inside your RM device, as shown here, now if you apply a voltage of opposite polarity, you will tend to like bring back these oxygen atoms or send these oxygen atoms to these oxygen vacancies and then recombine them. So not all of these kind of oxygen vacancies get recombined, only those which are close to the electrodes, they get recombined. And because of this reason, your reset voltage is, like, the magnitude of reset voltage is not same as the forming voltage magnitude, and you can never recover your original like virgin device. So that also let me write. So since you always have some kind of defects present, you cannot recover all of these defects. So you cannot go back to your virgin state as well. And also, for this reason, your HRS resistance, the resistance of the HRS is low as compared to your forming, like the resistance of device before forming. So the as deposited resistance, or let me just write it, add its as deposited resistance. So as deposited, you are in pristine state. You are in pristine state. Even when you kind of switched it, you performed forming, you injected defects, and then you apply some voltage to kind of recombine those defects. So even when you do that, you can recover only some of those defects, and because of that, your HRS resistance is kind of lower as compared to your forming resistance, because there are already some traps which can conduct, right? So this is something which is important to know. And apart from that, since not all of these like oxygen vacancies can be recombined, so whatever portion, so let me write that the portion of vacancies which do not recombine they tend to act like virtual electrodes. Since they can conduct, they tend to act like virtual electrodes. Now the problem with forming process is that a very high voltage is required for forming process for inducing these defects, because soft dielectric breakdown is not an easy process. You need to migrate your oxygen atoms. They need to be knocked off. And for that, you need to provide high energy. So this forming kind of leads to, energy inefficiency, or that is a part where RRAMs are very energy inefficient. So the forming process consumes a lot of energy. So because of that, what people want is, so let me write that. So what people want is a forming free device, because it's the forming process which consumes a lot of energy. And you can't even work without this forming process. So what this forming process depends on? So forming process or forming voltage. So forming voltage also depends on oxide thickness. So apart from depending on the material and the electrode combination, it also depends on oxide thickness. So 3 nanometer HFOX based devices have been shown to be forming free. So you reduce, your thickness of the device, you concentrate the electric field, and then you can also form, you can also achieve forming free devices. However, the best part is you need to form the device only once, and once it is formed, you can use it indefinitely. So let me write that point as well, because this is also important. So I'll write that point here itself. So forming is needed only once in lifetime of the device. So you form the devices, you fabricate the device, you form the device, and then you deploy it in the field. Then you don't need to invest a lot of energy to make this device work. Or the other way, which I told you, that instead of inducing it by voltage, you induce it by using limited precursor. I mean, use kind of a precursor, or you can also introduce defects while manufacturing. And you may know that introducing defects is way easier as compared to make something highly pure. So about the forming process in detail, let us go ahead and discuss about the reset switching mechanism, which is kind of the most controversial mechanism in the field of this resistive ramps. So there are different theories which kind of explain your unipolar or bipolar switching. So there is one theory which is called thermal dissolution model, which explains part of your unipolar switching. Then there is this oxygen ion migration model. That model explains your bipolar switching to some extent. However, there needs to be a unified model which kind of explains both of them together. So this model was given by Professor Shibeng Yu of GATEC recently, I think in 2015 or 16. So we will be discussing that as well. So what led to that model, or what led to the development of that model, was experimental observations. So the first experimental observation was, as I already discussed, the CAFM images showed migration of oxygen vacancies, oxygen ions, which kind of led to oxygen vacancies, oxygen vacancy based conduction filament, right? And they were able to kind of image this conduction filament in bipolar RM devices. And at the same time, the electrothermal simulations. So what are electrothermal simulations? So you solve thermal transport along with your electrical kind of properties, like you solve electrostatic equations along with thermal transport. So it's same as considering Seebeck effect along with solving Poisson and current continuity equation. So once you do that, the electrothermal simulations of unipolar devices or even the bipolar devices that showed that the local temperature due to current conduction through your filaments, through your conduction filaments, may lead, or the local temperature due to the current conduction through the conduction filament may reach several hundred Kelvin. So if the temperature around that conductive filament is so high, what will that do? That will further enhance diffusion or ion migration, right? So whenever temperature increases, the migration and all increases, right? So electrothermal simulations showed that local temperature can be very high. And regarding this bipolar or unipolar switching, the electrode material actually plays a big role. So if you see this table over here, you can see that in unipolar switching or RM devices which show unipolar behavior, you mostly have these noble metals, right? You have platinum, you have mostly platinum or ruthenium. So it's mostly symmetric. You can see that it's mostly symmetric. The top and bottom electrodes are mostly symmetric, and they are made up of some noble elements. So let me write that like that observation. So in unipolar RRAMs, what you have is you mostly have noble metal electrodes, and mostly they are symmetric, right? So let me write that as well. So they are noble metals like platinum or ruthenium, and they are mostly symmetric. And then what can you conclude about the bipolar ones? So in the bipolar ones, you can see that one of them is platinum, but the other one is kind of changed. They use titanium nitride or strontium ruthenium oxide as well. So in bipolar, they use one electrode as noble metal, but replace the other one with an oxidizable material. So this titanium nitride or titanium or these materials are oxidizable. So they replace it with oxidizable material. And now what are the other problems with platinum or these noble metals? So the noble metals are difficult to etch. So the noble metals, since they are not so reactive, they are also difficult to etch. So let me just write that. So they are also difficult to etch. And now, based on these observations, let us see how Professor Shimenyu came up with this kind of a unified approach. So, needless to say, since the CAFM kind of images told that there is exactly a formation of conduction filament, the forming leads to soft directed breakdown. And then what happens is the oxygen atoms which are knocked off form ions, and then they drift towards positively charged electrode, right? And which is your anode. This is shown in the first figure. So your oxygen atoms are represented by yellow here, oxygen ions basically. So they so the atoms get knocked off and these atoms form ions and they are then drifting towards your top electrode, which is your anode, at V forming. So this is what happens, and this leads to the formation of this conduction filament. But at the same time, what happens to these oxygen ions when they reach the electrode? So let me just write that. So if your electrode is a noble metal, then it won't react with your oxygen ions, and then these oxygen ions get discharged. These oxygen ions are discharged as neutral non-lattice atoms if your electrode is a noble metal. However, if your electrode is reactive, or if it's an oxidizable material, what happens is it leads to an interfacial oxide layer. It leads to an interfacial oxide layer close to anode, right? Now, regardless of whatever is happening, you have at the anode oxide interface, you have oxygen reservoir, right? Immediately after forming process. So immediately after this forming process, what happens is your oxygen atoms move towards your top electrode, and if it is noble element, then they are discharged as neutral non-lattice oxygen atoms. If they are reactive, then there is an oxide layer over here, interfacial oxide layer over here, close to the anode. However, in both the cases, you have oxygen atom reservoir close to the anode surface itself. Now, once you have this conduction filament which is formed, if you apply a voltage, current will flow, and the current in this low resistance state, current in this LRS actually flows through your conduction filament, right? So the current in LRS after forming will flow through your conduction filament, and that CF is located in bulk of the device, bulk of the oxide, right? That is also true. So it's located in the bulk of oxide, and this will lead to current flow. Now, what happens when you apply a reset pulse? So when you apply a reset pulse, so LRS is filamentary conduction, that is true. When you apply a reset pulse, if it is unipolar conduction, then V reset will also be positive. If it is a bipolar conduction, your V reset will be negative. So if it is a unipolar case, or what exactly happens in the reset pulse, regardless of unipolar or bipolar, what happens in reset when you apply reset pulses, the oxygen ions close to the anode, what they'll do? They'll migrate back to the bulk, right? And once they reach the bulk, once they encounter these conduction filament oxygen vacancies, what happens? These ions recombine with your oxygen vacancies in CF, and because of this, what happens? The conduction filament dissolves. So the CF dissolves. Now, what is different between unipolar devices and bipolar devices? So let me write that. So in unipolar devices, what happens is, because of the current flow, there is a Joule heating. So the Joule heating of the CF, what it leads to? It increases the temperature. And once the temperature increases, what happens? It aggravates thermal diffusion of ions, right? So as I told, as the temperature increases, thermal diffusion increases. So this Joule heating kind of increases your migration of these oxygen ions. Now what happens for bipolar? So in unipolar, it's actually the thermal diffusion arising because of this Joule heating, which leads to this conductive filament or the fast dissolution of this conductive filament. Now in bipolar devices, and one more point to note here is that this is happening when your metal is noble metal. Now your bipolar happens when the metal is oxidizable element, right? So once it's an oxidizable element, what we said was that there is an interfacial oxide layer. So there is a interfacial oxide layer. And the oxygen ions which are there at the anode, they have to move through this interfacial oxide layer in order to reach the conduction filament. So this interfacial oxide layer, in the case of these bipolar devices with oxidizable metal electrodes, what they do is, this interfacial oxide layer, this provides a barrier to the thermal diffusion process. So since there is a barrier to the thermal diffusion process, not many ions tend to come up with, and so let me show you that. So not many ions are able to come and recombine with these vacancies. And because of that itself, what we need is, we need a higher electric field or a higher voltage of opposite polarity to dissolve or recombine oxygen vacancies of conduction filament. So dissolving of conduction filament simply means recombination of those oxygen vacancies of the conduction filament with the oxygen ions which are kind of present at the reservoir, anode oxide interface reservoir. And at the same time, how we model this? So how we model this conduction filament? So how we model this is, it is modeled as a cylinder between the electrodes. So during the set process, you apply a larger pulse. What you will do is, you will increase the width of this cylinder of conduction filament. And since the width is increasing, what will happen? Its resistance will reduce. Whereas for reset process, we model this CF cylinder's height. So if the height is lower than the oxide thickness, so let me just draw this. So let's say this is one electrode, this is the other electrode, and we have modeled it. as you know, a kind of cylinder in between. If the height of the cylinder is small as compared to the oxide thickness, then we can say that okay, the filament has dissolved and the process has, or the device is in the reset state. So this is how they kind of model the conduction filament. And if you look at this curve here, you can see that, you know, immediately after reforming, there's a soft breakdown, and then we reach this state where the oxygen ions are kind of migrated towards your top electrode, and you have a conduction filament which conducts the current. Then you apply a reset voltage, regardless of whether it is unipolar or bipolar. What happens? These oxygen ions kind of migrate towards this conduction filament. If there is an interfacial barrier, the migration will happen at large voltage, or when the voltage is of the opposite polarity, and that is why you end up having bipolar states. And once this happens, the oxygen atoms occupy their lattice position, because now they have recombined with your vacancies, and so they occupy their lattice position. And what you end up having is dissolution of conduction filament from the bottom electrode. However, since there are some defects already here, I mean, there are some vacancies which are not kind of which have not been recombined. So this is called as virtual cathode, which we discussed earlier. And then again, if you apply, you know, the set pulse, what will happen? Again, these oxygen atoms will be knocked off, they'll go towards your anode, and then again you will end up creating this conduction filament. So this process is reversible. This process which is shown over here is reversible. However, going from this fresh sample or virgin state to this forming state, or you know, this set state, this process forming is not at all reversible. So once you form the device, you are sure that these defects are going to be there. Not all will be recombined, as I discussed in the previous slide. Now that we understand the reset mechanism and all, let us go and read about some of the popular RRAM stacks. So what are the most popular RRAM stacks? So mostly they are some transition metal oxides, and we don't have stoichiometric oxides, we have non-stoichiometric oxides, which we represent as OX. This first can be anything, but then we have OX. So we have HFOX, TiOX, tantalum oxide, we also have nickel oxide, then we also have like copper oxide, tungsten oxide. So these are some of the most, that aluminum oxide. These are some of the most widely studied transition metal oxides for RN devices. Now let us discuss few of them and their unique properties. So we discussed in the first slide itself that we have copper oxide based devices in the interconnects. I mean, we can have these in the interconnects. We can have tungsten oxide based devices in the sourced in contact plug itself. So these are CMOS compatible. Now, how do you fabricate these devices? I mean, how do you fabricate a MIM capacitor? So first process, you oxidize the metal. How you do that? There are several processes. However, you can also deposit the material. You can also deposit the oxide, metal oxide. What are the different processes by which you can do this? You have reactive sputtering. So this has to be RF sputtering, because with DC sputtering you cannot deposit metals. Then there is this PLD process. Recently people have also started using ALD for depositing these oxides. So let us first discuss about HFOX, which is one of the most widely studied kind of material for RF. Why this HFOX is more common is because, you know, in your modern CMOS devices, your gate oxide is no longer SiO2, but it has been replaced by a stack of SiO2 and HFO2. So because of this, because of its CMOS compatibility, and it's ready, I would say it's available already in your CMOS process. So it's very lucrative to utilize this for memory application as well. So it has been the most widely read stack. So let us talk about the properties of this stack. So the properties are, first of all, it's bipolar. So most of the HFOX based devices are bipolar. The switching speeds or the switching times are in the range of 10 nanoseconds. So that's ultra fast. The ratio of the on resistance, or I would say LRS, to the off resistance, that is the HRS, people have shown greater than 100. The ratio between the on state and the off state, that is LRS to HRS, people have shown that it's greater than 100 in HFOX. Then people have also shown that it shows an endurance which is greater than 10 power 6. That is also good. It's higher than flash devices. And the yield is high. Yield is high, or uniformity is more. So uniformity is one of the major problems with our RM devices. And since this HFOX gives you a high yield, so this is one of the most popular kind of RMs. And in terms of scalability also, people have shown 10 nanometer cross 10 nanometer working HFOX devices, and the thickness of HFOX, if it is reduced to 3 nanometers, then even forming free devices may be realized. So these properties make it very promising. So that's the reason why it has been studied more. Then the other class of oxide which people have studied is this ALOX. So this aluminum oxide is also CMOS compatible. And the best part about this is these devices give you a very low reset current. Since the reset current is low, so your HRS resistance is really high. It can go to some gigaohms. However, the problem is that if your HRS is really high, your LRS will also be high. So your LRS here is also in some mega ohms. So it's good for reducing static leakage. It's good for reducing your static leakage current, because your reset currents are in the range of some 100 nanoamps. That is actually good. Now another thing, or another stack which has been widely studied is this. It's this NiUX. So let me just write that as well. So it's NiUX. So the best part about NiUX is it's unipolar. Why I call that unipolar is a good quality? Because for unipolar devices, even diode selectors work perfectly fine. So diode selectors have got a low area as compared to your MOSFET selectors, and as such you can realize a small area memory cell. So that is why your NiUX is also promising. However, for unipolar, there are some constraints which I already told you to find out. So one of the constraints for unipolar is that the distribution of set and reset voltages, I mean the switching voltages, across the entire array. You have different devices, so you have all of these devices show different set and reset voltage because of process variations and all those effects. However, for a unipolar device, you want that the distribution of set and reset voltage is narrow, and difference between the two is large. So these are two requirements that you want for a unipolar kind of device. Then another stack which is very famous is tantalum oxide. So let me just write it as well. So we also have this tantalum oxide which is really famous. And why is it famous? So the tantalum oxide actually shows you high endurance. How much high? So people have actually shown greater than 10 power 12 to 10 power 13 cycles of endurance, which is way more than your 10 power 5 or 10 power 4 of flash. So what happens in TOX based memories is that your TOX is actually existing in two phases. So one of them is your tantalum oxide, which is TaO2, this is a conducting phase. So this TaO2 is conducting, and it also exists in Ta2O5 phase. So it also exists in this Ta2O5 phase. So this Ta2O5 phase is insulating. So in this TaOH memory, oxygen migration takes place and it changes between these two states. Since its endurance is very high, can you suggest a potential application for this? So if your device is offering very high endurance, it can be used for embedded memory, right? Okay, so this is all for this lecture. We'll read more about these RM devices in the next lecture.